I want to give people a better insight into how AM radio works and what it actually means to tune a radio with simple examples and easy to understand visuals. Imagine a local radio station which broadcasts classical hits. We'll call this station Channel A. They broadcast by channeling the raw audio waveforms from the music directly into their broadcast antenna. Everyone in the area can listen by channeling the raw signal from their radio antennas directly into their speakers. This system works alright until another channel, which we'll refer to as Channel B, decides to debut their selection of recent D&B hits. Channel B broadcasts using the same method as Channel A, but the signals effectively sum in the air, and the listeners receive the combination of both signals. The D&B fans don't want to hear Channel A, and classical music enjoyers don't want Channel B playing over their symphonies. This is detrimental to the business of both channels, having each lost all of their listeners. So they decide to work together to develop a potential solution. So how can Channel A and Channel B share the same airspace, such that listeners can choose which channel to tune into? I will simplify the audio for the sake of visualization. These two waves are the signals for Channel A and B, which represent the audio each channel wants to deliver to their listeners. This third wave is how the two signals add in the air with their current system. An engineer working at Channel A has been studying filters and has an idea. But first, what is a filter? Put abstractly, a filter is a small circuit that, when fed a signal, can attenuate or diminish frequencies above or below a specific cutoff frequency. Here is the equation for a signal with three components at different frequencies: 10 Hz, 27 Hz, and 51 Hz. A filter that attenuates frequencies above the cutoff is called a low-pass filter, as it only lets lower frequencies through. If I low-pass filter this signal at 40 Hz, the 51 Hz component, being above the cutoff, is eliminated, while the 10 Hz and 27 Hz components pass through. Conversely, a filter that attenuates frequencies below the cutoff is called a high-pass filter. If I high-pass filter this signal at 20 Hz, the 10 Hz component, being below the cutoff, is eliminated, while the 27 and 51 Hz components pass through. The engineer from Channel A thinks that both channels should pick a unique high-frequency cosine wave, called a carrier frequency. He recommends 60,000 Hz for Channel A and 50,000 Hz for Channel B. He then asserts that each channel should multiply their signal by their respective carrier frequency before broadcasting. The product looks similar to the original signal in fashion, but if you look closely, you'll notice that it also oscillates uniformly at the carrier frequency. The product is essentially the carrier frequency with its peaks modulated to the height of the signal. This product is called amplitude modulation, AM for short. The engineer states that if both channels broadcast their amplitude modulations at their respective carrier frequencies, once they add in the air, it is trivial to isolate either channel. One simply has to filter to a tight window around either carrier frequency of their choice, and only the amplitude modulation at that carrier frequency will pass through. The engineer proposes releasing a new line of radios with a dial that allows listeners to choose which carrier frequency to filter to. This is what is commonly known as tuning a radio. However, once the radio has filtered to the amplitude modulation of the channel, it still needs to convert the amplitude modulation back into the original signal. There are two methods of this. The simpler method is called an envelope detector, which is a simple circuit often consisting of a diode and capacitor, which simply traces the peaks of the AM wave. It's often deemed a close enough approximation for high carrier frequencies. However, there's a much more elegant method called a product detector, which makes use of an important trig identity. At the moment, our amplitude modulation can be presented by the product of the signal, S of x, and the 60,000 Hz carrier wave represented by cosine 60,000 times 2 pi. We can then multiply the amplitude modulation by itself with the carrier frequency again, effectively giving us the signal times cosine squared at 60,000 Hz. Using the trig identity cosine squared x equals 1/2 plus 1/2 times cosine 2x, we can replace the cosine squared in our expression and rewrite it as the signal times 1/2 plus 1/2 times the cosine at 120,000 Hz. Using the distributive property, if we distribute the signal function across the sum, we end up with this. However, if you look closely, we have the signal itself with a very high frequency component added to it. Recalling how filters work, with the use of a simple low-pass filter, we can eliminate that high frequency component. We'll choose to low-pass filter to below 20,000 Hz, which is the highest frequency the human ear can hear, and therefore the highest frequency we need to preserve in music. After filtering, we're left with 1/2 the signal. Finally, with some simple amplification, we have an exact match of the original signal for Channel A. The engineer from Channel A has successfully solved the conflict, and each channel can now broadcast on its own frequency to its own listeners, who can tune in by choice.